The last programming system that we will write will be a tiny version of the world's most widely used programming language, which is Excel. I'm not joking. If you look at Excel and spreadsheets more generally as a programming system, they have a number of very interesting properties. So it's worth looking at them in our course as well. First of all, is Excel really a real programming? Well, you can answer this question in various ways. First of all, Excel is Turing complete. So there's this nice example at Feline Hermann's blog where she describes how you can encode a Turing machine in Excel. And this is not using macros. It's actually just using this drag down feature of Excel that we will look at later on. So you define a row that represents your Turing machine, and then you can drag it down and you get a Turing machine emulator. This is not a very useful answer. It's theoretically sound, but it doesn't tell us really much about Excel. Excel is also very widely used programming language. Now, of course, a lot of people use Excel just for recording data. So the fact that it has millions and millions of users doesn't tell us much. But there's still a lot of people who use Excel to write some formulas. And this is an interesting use because to a larger or smaller degree, people using Excel are actually programming. They're writing some computations. So maybe it cannot do everything that you can do in a large programming language, but the way it works is something that we can use as an inspiration. So what is it that makes spreadsheets interesting as a programming system? First of all, they are very accessible. People who have no programming skills can use spreadsheets. And it's worth thinking about why that's the case. I'll talk about some of these reasons later on, but you work in this easy to navigate grid, you always compute with concrete values. And this is something that matters. The grid is something that kind of embeds the program in some space that people kind of intuitively can understand. It gives them the freedom to organize their structure, their code. You also have the same environment, the same graphical interface when you're editing, creating a program, and when you're viewing it. So if you just, someone sends you a spreadsheet and you look at it, by doing that, you are already seeing the program, the programming environment, and you can learn a little bit how spreadsheets work. And another thing that's very interesting in spreadsheets is this live recomputation, where as you make any edit, everything that depends on the value that you've changed changes and recomputes immediately. So this gives you, again, some good ability to see what's going on in your program. And we've done some work together with Joel Jakubovic on figuring out what's the key aspects of programming systems, what makes them interesting, and we use spreadsheets as one of our examples, along with a lot of other things, including the web platform, Smalltalk, and so on. So if you're interested in what we think makes spreadsheets interesting, then you can look at more details on our technical dimensions of programming systems, which is both a paper and an interactive web page with this large grid of properties of different systems. Before we get started, I will show you a little bit of Excel. Now, I'm sure many people have seen Excel already, so this is not really teaching you Excel. What I'm trying to do here is more to illustrate the interesting aspects. So I have this table which lists different continents, and then it lists the population in 2024 and the area of the continent. I'm not using any fancy features in Excel. In Excel, you can mark a region as a table, and then if you do that, Excel will actually name the table, it will name the columns, but I'm not going to be using any of that. I am interested in just the raw grid with numbers and references using the indices. So what I can calculate from the population and the area, for example, is that I could compute the density. And the density will be the population. No, I want the area divided by the population. So you can see I had to figure out which way this should go. And the nice thing is I will see immediately if I got it right. So is this right? Well, no, this is wrong because I got it the wrong way around. So what I really want is what's the number of people per square kilometer. This is one of the nice things about spreadsheets. You get this immediate feedback. So I've done one thing here, and the other really interesting thing in Excel, and that's something we will try to implement, is that, okay, so I've got this formula. Excel nicely highlights the cells that you're referencing, but I can drag the formula down, and what happens here is that Excel will automatically update the references in the formula. So here, as I drag down, the references got updated relative to the offset, and so I'm computing the density of the corresponding continent. Before we go further, I will also add a total. So you can write formulas in Excel. This is something that people have already seen, where I can reference a region and, for example, sum the total population. I can sum the total area as well. And now I can extend my formula to the whole world. So this is one of the interesting aspects of the Excel programming environment. And what's really going on here, like if you think of it as a programmer, I've sort of defined a function called density that takes the population, takes the area, and calculates the density. And then I applied it across the whole table. But I didn't do it by writing a function. I did it by writing a concrete computation and then extending it. And that's an operation that lets you think much more about the concrete values than about some complicated abstractions. So this was one example. Now, let's say that I want to calculate something else. What I want to calculate now is ratio. So how much, let's say, how many people live in the continent compared to the whole world. So if we take the whole population, if we take the actual number divided by the whole population and multiply that by 100, then we get our result. And again, I can see immediately what the result is. I can apply some rounding function to make this look a little nicer. And I see that in Asia, there's roughly 60% of people from the world were living there in 2024. All right, so now I want to extend this formula to the whole world, all the continents. And when I do that, I get an error. What's going on here? Well, I had a reference to the row, the population for the current continent, and the population of the whole world. And when I extended it, Excel did what it did before, which is change the relative references. And so it changed the blue one for the continent, and that is what we want. But it also changed the red one, which was referring to the population of the whole world. So we don't want that. And there is a way to prevent this in Excel. If I mark this with $sign, and you can do that both for the row and the column reference, then this is fixing the dimension of the reference. So this says when I extend it, keep it as it was. And now I can do this, and it actually extends as I wanted. So now we get the percentages for all the individual continents, with Antarctica still scoring the 0. So this is a demo of how you work with Excel, and as I was saying, I'm not showing this because I don't think people have seen Excel before. I'm showing it because it illustrates the interesting aspects of Excel that we will try to re-implement later on. So what is good and bad about spreadsheets? There are many good things. They let you do this quick exploration where if I have a spreadsheet and I change some data, then I will immediately see how it affects the results. If I go back to my spreadsheet and suddenly there's let's say a million or maybe 100 million aliens landed in Antarctica, I will immediately see how it affects the result. If I add even more aliens, then suddenly Antarctica has 55% of the world's population. This is, and you see this as you change the value, all the affected things update live. So this is this live property of the system where you can immediately see what's going on. The other good thing is this working with concrete values, where I can write the computation against actual numbers, not against some symbolic variables. And another thing that I will get back to later on is that it's very easy to learn. There are, of course, bad aspects of spreadsheets. An interesting recent one is the implicit data conversions. So there's a lot of biologists who use spreadsheets and they work with genes, and it happens to be the case that Sept2 and March1 are gene names, and when you load this into Excel, Excel parses this as a date and converts that to a number. And so your septin and membrane associated ring finger genes suddenly become numbers. And this is something that has caused actual errors in scientific papers. Another case of an error was the case of a paper called Growth in the Time of Depth. And this is an economics paper that has partly inspired governments to respond to the 2008 financial crisis with austerity, because it was saying, if you cut expenses, your economy will recover more quickly. It turns out that the paper had a number of errors. Some of them were more subtle modeling errors, but one of the errors was caused by the fact that when calculating some sort of average over a table, the authors used this sort of selecting a range operation to specify the argument, and they just missed the first 5 countries or so. So, and this is something that wasn't really visible in the code. It was just some range somewhere in a formula. So there's a drawback in how Excel hides the code from you as well. So one of the interesting things about spreadsheets is how they quickly reevaluate the data. And this is something that has a little bit of a confusing terminology around it. So to make things clear, people sometimes talk about exploratory programming, and by this we can understand the ability that you can quickly change things, see how the results adapt, and you can do your thinking interactively with the programming. So you write some code, do a little bit of thinking, see what it does, revise your code, and do that in some iterative loop. And this is something that you do all the time when you're using Excel. The second term is live programming, and this refers to the fact that when you make a change, you see the results update immediately or almost immediately. That's something that you have in spreadsheets as well. When you change a number, the depending things will recompute, but it's also a thing that exists in various other experimental programming environments. Another term that you might hear is live coding. And this is something that people often use specifically when they talk about live coded music, using programming systems where you can write some code to describe your musical composition and or music control a synthesizer. And what these systems do is that you write your code, run bits of the code, and it updates this synthesis process that's going on in the background live. So it's again live updating, but typically in the context of musical performances. And finally, interactive programming is another term that you might often hear. This, I think, typically refers to the idea that you work in some sort of stateful programming system that you can modify by writing and running some commands. For example, in Smalltalk, when you are in the Smalltalk environment, you can use the browsers to edit the state of the objects, and that is interactive programming. So spreadsheets are exploratory and live. This means that it's easy to fiddle with the data and you see the results almost immediately. And those are two really interesting, really valuable properties of spreadsheets as a programming system, because it means you can easily see what's going on and understand your problem while writing the code. The other interesting thing about spreadsheets is how they deal with abstraction. So I said before that you can think of density as a function, and so this would be another example where if I wanted to write this relative calculation of population ratio in JavaScript, I would have to write a function. But when you're writing a function, all you work with are these variables. They're sort of symbolic values that represent some value, but you have no idea what actual values you will get. And this means that you don't see which value is the bigger one and which way you should divide things. And spreadsheets don't, when you do abstractions in spreadsheets, you don't have to do this. You don't write functions. You construct a formula against concrete values and then extend it to work across a range. So you're constructing this abstraction starting from a concrete value. And that's exactly one of the interesting technical dimensions of programming systems that we talk about in our work on the technical dimensions. So what's going on in spreadsheets, it's much more like this idea of concrete programming. And this is something that first appeared in 1961 in the context of industrial robots. So the robot that you can see in the picture here, this is a robot that you programmed basically by dragging the arm and the robot in some sort of recording mode would capture what you are trying to get it to do, and then it would just replay the actions. So it was a very basic macro recording facility that was used there. And of course, this is something that then people thought about in the context of programming languages. And in the introductory talk, I showed you Pygmalion, which is one of the programming systems that tried to think about programming through this macro recording perspective. So you enact some operation and then it can generalize and reapply those operations. And the drag down operation in spreadsheets is basically a variation on that. Another interesting thing that makes programming in spreadsheets concrete is that it also supports programming by example. This is something slightly different, and this is a feature where you can give spreadsheets a series of input-output examples, and it can try to figure out how to generalize from the input-output pairs to something that it can apply across other values. This is implemented in Excel under the name of flash fill, and as an example, I could try to add another thing to my table and turn the name into some sort of code. So if I say AS and AF here, then I can go to the Data tab and find flash fill. And what this does is that it looks at the two examples I've provided, and it figures out, it synthesizes a function, a bit of code that does the conversion. In this case, this was quite easy because it has to figure out I'm taking the first two characters and making them uppercase. If I, for example, just say A as the first letter, then try to generalize. Using flash fill. Now it doesn't work so great. So I got the first letters here, but then for multi-word names, it synthesized code that keeps the first word as it was and just trims the last lowercase bit of the entire phrase. So we don't like that, and what I can do is change the samples. So if I keep A for Asia but NA for North America and run flash fill again, now it synthesizes a bit of code that presumably takes all the capital letters from the name. So this is a very interesting feature in spreadsheets, or in Excel specifically. We're not going to try to implement this because it fundamentally depends on figuring out synthesizing some code. So this is a bit more challenging, but it's a very interesting approach that becomes possible in an environment like a spreadsheet. The last aspect of spreadsheets that I want to talk about is how people learn spreadsheet systems like Excel. There is a paper that looks at this, and the conclusions that the authors make is that there's basically two ways in which people learn. One way is that they learn from existing spreadsheets, because if someone sends you a spreadsheet, you can look at the formulas and see how the computation has actually been done. And this is something that's possible because the formulas are just embedded in the spreadsheet document itself. But that's not the case typically for compiled application, where you just see the application, the interface, but you have no way of figuring out what code is behind it. So the fact that the code is embedded in spreadsheets is something that enables people to learn how things are created. The other interesting aspect of learning something like Excel is that the second typical method is going to the local expert. So every office has this Excel guru, and that's a person who you go to whenever you're trying to figure out something hard in Excel. There's some functions in the Excel formula language that are confusing, and they typically need an expert. But there's also aspects of spreadsheet of Excel where, unlike the formula language, they don't leave a trace. You don't see how things were created. If you insert a chart in Excel, this is done through a graphical interface, but the graphical interface leaves no visible trace. So you don't know where people clicked and how they achieved this, and then you need to go and talk to the experts. And one of the very visible aspects of spreadsheets that interesting is that it all exists in this grid. And this relies on the fact that humans are very good at working with space. In some of the earlier talks, I mentioned the Boxer project, and that's again a system that tries to leverage space. So normally programming is not something that you do in a spatial environment, and spreadsheets take a different approach. They really have this grid where you have to do all your programming. And the grid as a structure is somewhat limiting. You can't have richer structured data representations, but it's also something that's very easy to understand, and it's also something that lets people allocate different bits of space in the spreadsheet for different things that they want to compute with. So it lets people structure their data, maybe in a very primitive way, but in a way that helps them work. So what can we learn from spreadsheets if we look at them as a programming system? First of all, it's an interesting programming system that is actually accessible to non-programmers. Lots of people are able to create things with spreadsheet. It is an environment that gives this immediate live feedback. As you're changing your code, you see immediately what it does. You can create abstractions not by writing functions, but by manipulating concrete data and generalizing. And then there's this idea that the programs exist in some sort of space. All of these are available in spreadsheets, but you can also imagine that many of these features could exist in a normal programming language that's not a spreadsheet. And there's a couple of demos that Brett Victor has created, which are looking at how this might look. So the various demos that he created are exploring what could programming look like if it was more live and more interactive, and so on. So this is worth looking at if you find spreadsheets interesting but want to see how this might work in a real programming environment. So what are we going to do in the course? In our TinyExcel. So we're not, the first thing is we are not going to write the user interface for it. This is unfortunately a bit more difficult, so that's out of scope. But we will still work with a representation that is this two-dimensional space with references. And we will implement some of the interesting aspects of spreadsheets, mainly this drag down operation that lets us generalize a formula to an entire column or over multiple rows. We will implement these relative and absolute cell references using the dollar sign to make sure that the extension works correctly. And we will implement an evaluation engine that will support this live updating. So when you change a value, the change will propagate throughout the spreadsheet. So this is kind of doing the backend implementation that's behind this nice front end, which is left as an exercise to the reader.